Hello, today I am going to present a geometrical proof for Borsuk-Ulam theorem for S2. Borsuk-Ulam theorem states that if f is a continuous function from Sn to Rn, then there exists an x in Xn such that f of minus x equals f of x. So Borsuk-Ulam theorem for S2 is what we get when we put n equals 2. I'll come to this theorem later. Right now, we need to prove some lemmas in order to prove the Borsuk-Ulam theorem for S2. So the first lemma will be the winding number for an odd continuous map from a circle to a circle is odd. That is, if f is a continuous odd function from S1 to S1 and f of S1 winds around circle n times, that is of course e raised to nit, then n is odd. So as f is an odd function, minus of x should map to minus f of x, and a pi a rotation of x0 should map to n pi a rotation of f of x0 because winding number is n. So thus e raised to pi a is minus 1, minus of x0 should map to minus of f of x0. So e raised to n pi a is equals to e raised to n pi a should be equal to minus 1. So which implies n should be an odd number. So that out of the way, we can continue to our next lemma. So the next lemma will be there does not exist a continuous odd map from S2 to S1, that is S sphere to circle. We are taking the proof by contradiction approach here, that is we have assumed such an f exists. Now we have defined 3 unit circles which are subset of S2. C1 will be in xy plane, C2 will be in xz plane, and C3 will be in yz plane. All of them are centered around 0. So let's assume this is the S2 and this will be the C1, that is circle in the xy plane. This one will be C2, that is circle in xz plane, and this one will be C3, which will be in yz plane. So this is how it will look like. So as they are circles, obviously there exists a bijection from S1 to Ci. So we can call them Gi for each Ci, the bijections of course. As you can see, f restricted to Ci composition Gi makes a map from S1 to S1. So from our lemma 1, they have odd number of windings, and Theorem plus or minus 1 makes up all the odd numbers. We know that G3 is a bijection, so let x0 is a point in S1 that points to 0, 0, 1, which is the z equal to 1 point in z axis, and let y0 be the image of 0, 0, 1 under f. As the composition map is from S1 to S1, a pi by 2 rotation should result in Theorem plus or minus 1 pi by 2 because the number of windings is Theorem plus or minus 1, and this is of course y0, f restricted C3 composition G3 of x0, and multiplying Theorem and pi by 2 makes up 2m. So 2m pi I is e raised to 2m pi I is obviously 1. So all that left is to take care of plus or minus 1 pi by 2i. So e raised to plus or minus 1 pi by 2i makes up plus or minus 1 e raised to pi by 2i. So all in all we get this. So as we are taking 0, 0, 1, this is the point 0, 0, 1, and C3 is a circle in yz plane. this is the circle in y-z plane. We can see that a pi by 2 rotation should come in plus or minus 1 of on y-axis. That, as you can see, there are two common points between both circles, and that is 0 plus or minus 1 0, and on pi by 2 rotation it will come to either one of those. It doesn't matter which one. So in terms of visualization, we can just take it as 0 1 0. So this will be the pi by 2 rotation. Now on to the next circle. As f already mapped 0 0 1 to y0, the restriction of C2 doesn't alter it because it's just a restriction of f. So mapping should be same. So x1 G2 maps x1 to 0 0 1. So this will be as previous y0, and the conversion is map from s1 to s1. So just like the previous one, we can map this to plus or minus y0 e raised to pi by 2i. Nothing new here. So just like before, circles C2 and C1 meets at 2 points plus or minus 0 0 1. So on pi by 2 rotation, they meet here or here. So for easy visualization, we can take it as this point. That is, on pi by 2 rotation, let's take it that this comes to here. As you can see that pi by 2 rotation of the first point is a positive or negative of the second point. That is, a pi by 2 rotation, which will be like this, will be a positive or negative of this point. So if we have taken this the point as this, it will also be same, because the pi by 2 rotation is plus or minus. We are taking it as plus or minus, so it doesn't matter which point we choose. So obviously pi by 2 rotation of this point will give us this point. So moving on to the last circle, C1. This is a point in C1. So just like the previous ones, we can rotate this point by 4m plus or minus 1 pi by 2. But we also have the value of this point, which is given by the C3 circle, which will be y0 plus e raised to 4m plus or minus 1 pi by 2. This is y0 obviously. So this makes us y0 e raised to 8m plus or minus 1, then again plus or minus 1 pi by 2. The 8m is cancelled because it becomes e raised to 4m pi I. So all that left is 2 plus 1s. So that makes plus or minus y0. So the rotation of this point, the image of the rotation of this point points to this, but the image of this point points to this. which is given by C2, but both of the points are same, so their image should be same because f is a function. As they are y0 is as y0 is in S2, y0 is not an origin, so these cannot be same. So this contradicts our assumption, and therefore there does not exist a continuous odd map from S2 to S1. Now on to our main theorem. Borsuk-Ulam theorem for S2 states that if there exists a continuous map f from S2 to S1, then there exists a point x in S2 with f of x equals f of minus x. This is a typo. This is a typo. So we are again going with the contradictory proof. So we have assumed that there does not exist an x, so that f of x is equal to f of minus x. So these can never be 0, which means g of x is well defined. As f of x is continuous, g of x is continuous. As f of x is a point in R2, this becomes a point in S1. G of minus x becomes f of minus x minus f of x divided by modulus of f of minus x minus f of x. So that will be minus of g of x. But according to our lemma 2, g doesn't exist, which is contrary to our assumption. Therefore, there exists a point in S2 with f of x equal to minus f of x. Thank you. There will be a link down in the descriptions for this PDF. You can check it out if you want. Thank you.